So good morning. Let me comment on, I'd like you to write this paper for the course. And it occurred to me it'd be very nice if you learn to work in teams. So work in the teams, right, and work and write in the team. Is okay. So if you would like to do that, it's not only okay, it's maybe a good idea. Now, if there's only one team for the entire class, but just some reasonable size team, friends and you work together and write something. So one of the things that I thought yesterday was completely elementary is, in my mind, a little bit more difficult, and so it is in any case very classical. So let me just write a picture of yesterday's, a picture of the S and invariant theory for its basic representation on the polynomial algebra just by permuting the indices. So we talked about yesterday. Let me just complete that a little bit, and I think you would enjoy thinking about it. It's a very interesting topic, maybe not now, but maybe later. So just recall that, let's say for n equals 3, you have line notation. So the line notation, permutation, is of the form. I did the example yesterday. This is line notation for permutation sigma, and this means sigma of 1 equals 2, sigma of 2 equals 1, and sigma of 3 is equal to 3. That's the notation. And so this, so sometimes I write 1, 2, 3 here. So 1 goes to 2, 2 goes to 1, 3 goes to 3. And the action on a polynomial, sigma of a polynomial, the way I set it up, z1 through zn, is just the polynomial with the permuted indices, sigma of 1, sigma of n. So for example, in 3 variables, the polynomial z1 to the 8th, z2 to the 14th, z3 to the 7th. Well, z1 goes to 2, so that's mapped to z2 to the 1 goes to 2 to the 8th, 2 goes to 1, so z1 to the 14th, and z3 stayed fixed. So that is the representation. And representation means that it's acting by linear transformations on the polynomial algebra. That is obviously a fundamental thing in mathematics. I mean, you don't need to even talk about it, right? It's completely obvious. You get polynomials, you permute indices. It's completely clear. So the picture of this thing is very interesting. So step one in the picture of this thing is the topological quotient. So you're interested in the invariance. So we are interested in invariant theory. Invariance. Whatever that means. And the first thing you do is you do the topological quotient, which we talked about in quite a bit of detail, of any group. Well, so far we only know about it by any, so it exists for any finite group. Well, it always exists, but it's not, it's maybe horrible. You've seen it, it's not Hausdorff and so on in the quotient topology in some cases. So for a finite group, it's quite reasonable. Let us recall, if you have X, for example, T4, I like T4 or Hausdorff or whatever you like, for a finite group, you make the quotient and you put this with the quotient topology, you get whatever you want here, positive. So whatever, it preserves the topological condition. And this mapping is continuous. That's almost trivial, right? It's almost just a matter of it's the definition of the quotient topology, right? It's almost, in my mind, it's not difficult. Okay. So that's that. And then, of course, the invariant functions, invariant continuous functions on X are the same thing just by the isomorphism pulling back functions. This is simply the functions on the quotient, continuous. Okay. That's a perfect picture from the point of view of top topology, right? Upstairs, downstairs, everything pulled back, perfect. It's a very easy matter to handle continuous functions. But quite frankly, I think continuous functions in this context are not so interesting. Right? It's not as interesting. So let me then put this picture here. I hope I can fit it on here. We have the Cn, and we're interested in invariant functions. So we make the Cn quotient, the topological quotient. I'll try to draw this big enough. The topological quotient, Cn modulo the symmetry group. That quotient is what we talked about here. That's what I mean by that. It's the orbit space, you have the quotient topology, all that stuff. Cn is a wonderful space. It is a vector space. It is a wonderful space for almost every subject I know about. I mean, it can't be better. In particular, it's a wonderful space for polynomials, and it's therefore a wonderful space for this subject called algebraic geometry. Yes, or convergent power series, globally convergent power series. Maybe that's complex analysis. Yes. So it's a wonderful space, and you took a wonderful space and you made a quotient by this group. And then you say, hey, it's great. That's T4, right? Or Hausdorff, or something like this, right? That's nothing. You want much more. Yeah, you want much more. So we would like much more than Hausdorff. So this is, let me just write here, this is a topological quotient. And we want more. And the trouble is, all we know is this mapping pi here, a priori, is just some continuous mapping. Right? You can imagine how bad an arbitrary continuous mapping could look. Right? So we use the averaging operator to somehow construct pi in a constructive way, averaging polynomials. This is standard. To average good functions and get good functions. So you see, this is related to the invariant functions on x. So if we average good functions on x, you get good functions on the quotient. Functions you can handle. Right. If you do this in physics, you immediately find differential operators like the Laplacian and so on. It's really, really very, very important. So you average good functions. So for example, we average the function z1, and we get the average function that we average is just you average it. And then we average z2, z1, z2. And you get, well, all possible products. Let me put in here zi, zj, where I is not equal to j. You get all possible products, I less than j if you want to make it unique, and so on. And finally you average all these very nice, obvious monomials. Monomial degree 1, monomial degree 2, monomial degree n, and n variables. You're running through the basic objects in this polynomial algebra, the homogeneous polynomials of degree 1, homogeneous, well, the constants are someplace, but I somehow have suppressed them out of my brain. Homogeneous polynomials of degree 2, and so on. This final thing is just the product. Of course, I've suppressed the coefficient. As you know, I motivated this from probability theory to make this a probability averaging process, expected value averaging process. So, but I suppressed that number, and these things are called the elementary symmetric functions. Yesterday, they appear as coefficients of polynomials, but I would like to. I thought about it a bit. I would like to use a better notation. I will call this S1, and I'll call this S2, and I'll call this Sn. And then you say you really believe that that this really gives you the quotient. So what you do is you consider a map S to Cn, which you hope gives the quotient. In other words, S is the map S1 through Sn. You bundle together the obvious things that you got by this, bundle together in a map, S1, S2, S3, S4, and so on, and you get a map. And then some guy told you that was sort of arbitrary in some sense. And so this guy is living in Cambridge, Massachusetts. You see I'm American, I said Cambridge, Massachusetts. Living in Cambridge, England, in the 17th century, thinking about these problems. There's difficulty of invariance of this thing. This guy averages Z1. He said, well, I'll average it and I'll get the same thing you get. Z1, so on, so on, so on. Of course I'll get the same thing you get. It's averaging. But then I'll average Z1 squared. I hope you can read that writing so small here. You get Z1 squared and so on. And then I'll average Z cubed. It's even easier to write down, quite frankly. Z1 cubed and so on. And finally, we'll average Z1 to the nth power, and that's just Z1 n plus up to Zn to the n. And this guy in Cambridge, England is called Newton, and so we call this the first Newton polynomial. Usually it's written big, but maybe I'll be consistent, write it small, n1 through nn. And this is sort of an obvious way to get all these invariants. So you get another map, n, which is, if you have put all the Newton functions which are invariant, n1 through nn, and you get another map to Cn. So far, so good. Right? So far, so good. This is just a matter of writing these things down. Right? Okay, and then I thought about it, of course, during the night. And then, of course, there are elementary ways, geometric from my point of view, of showing two basic facts. Two basic facts are, and they're related to nice remarks of people here in the audience, so related to the fact that Nicholas mentioned, he originally said, well, that should be an open mapping or something like this. Yeah.
I think it was Martin.
You mentioned that should, yes, yeah, you mentioned this should be an open mapping. In fact, using complex analysis, you can see that this mapping in the usual topology is an open, these mappings are open mappings. What is not so obvious, but what can be proved, is that these mappings are surjective and that they separate orbits. So these mappings have wonderful conditions. You should think what they are. They separate the orbits. They're open mappings. They do everything. They're a wonderful thing. And so what you can easily prove then is the following fact. That this, you see, they're invariant. So there's a map from the invariant theory to invariant theoretical quotient, the topological quotient, which is bijective. And there's a map here from this invariant theoretic quotient, which is bijective because these are invariants. So you have a beautiful diagram. And in fact, then you get a map from here to here, or here to here, it doesn't matter, it's bijective. And then the wonder happens. This is a bijective algebraic mapping from one good space to another. Bijective algebraic mapping from one good space to another, and therefore it's an isomorphism, and that states that the symmetric polynomials and the Newton polynomials are just functions of each other. So this is a beautiful, this mapping is just topological, this mapping is just topological, a priori, but this mapping is algebraic. An algebraic identification of these things. This is wonderful. And not only that, if you had another, let's say another, now I can identify these two things, it doesn't matter. If you had some other invariant, so let P be another invariant. So let P be a polynomial invariant, invariant polynomial. And so you might even think that you have more invariants if you make the adjunction of this P to the symmetric polynomial, for example, and you get a mapping to some say, let's call this Y, which you can show is an algebraic subvariety of Cn plus 1. And because there is obviously a map here, just forgetting the polynomial, and you check around here, this mapping is bijective, and therefore it is an algebraic isomorphism. Now, I'm sorry, but that's the picture. Right? But this is a completely general picture. Now, it's too much for this poor guy, from the beginning guy who's really interested in mathematics. He's a computer scientist. But it's pretty interesting, right? You write down all these obvious invariants, right? I bundle them up in a map, S, or bundle them up in a Newton map, N. Instead of saying you can express one in terms of other, because they're algebraically equivalent, and they express, every invariant can be expressed in terms of any of these things, right? Yeah. And I think you could, if you work hard and think about it and check the literature a little bit, And talk to Martin a little bit, because he's interested in this stuff. We were talking last night about this stuff a little bit. Talk to me a little bit about it. You can prove everything I just said. Okay? Yeah. And if you can do that, so this is a completely classical situation. This is a completely classical situation. I mean, the name Newton should indicate it's a classical situation. I mean, he really knew this. In 1600 something. That's not in his case. I don't know exactly his dates, but keep in mind he's more or less cotemporal with Galileo and so on, people like this. I mean, this is really a long time ago, almost 400 years maybe. In mathematics, it's a long time ago. It's not as far ago as Euclid, but Newton was interested in this. And then if you're wanting to be a mathematician or a physicist or anything that way, you should understand this first. And you say, my God, this thing here is really very general. Right? So you say, well, the first thing is I should say let G be a finite group represented on a complex vector space, of course finite dimensional, V. It's easy to see, very easy to see, that every finite group has a representation on a complex vector space. There is no problem getting these. The problem is understanding all these representations. That's called the representation theory of that finite group. Understand all of these representation theories. Given a representation, you certainly want to understand the invariant theory. That's the simplest first thing to do. Right? You want to understand this quotient. So you say that's okay. You look at V, and you look at the abstract invariant theory. Yeah? And now you begin to think about what is that? That's just topological as nothing. Right? And now you begin to think about, well, somehow maybe you have other invariants here, like the symmetric polynomials. I'll put a hat here, who knows? But you should create them by averaging. Right? You should create them by averaging over the group. That's the obvious way to get invariants. And so you average very nice monomials here. The obvious thing to average are monomials. Our obvious thing to average here maybe with some Newton thing. There are all sorts of ways of averaging, and you go get to something here where it might not be a vector space. We're extremely lucky there. This is just some x, or let's call it y because this is some y. And this is some z. And you know y and z are topologically equivalent to this, and there's a bijective map therefore between y and z are algebraic. There's a bijective algebraic morphism, and therefore is an isomorphism. You understand what I'm saying? There are hammers in certain subjects, and one of the subjects is algebraic geometry. The hammer is if you have an algebraic variety, y in this case, and an algebraic variety z in this case, and they satisfy minimal conditions that you could, I don't want to bother you with the conditions, satisfy minimal conditions. I mean, here's Cn, but they won't be in general Cn. And a bijective map, algebraic map between them is an isomorphism. That's that's an example of a mega theorem. It's not hard to prove. So I don't want to dwell on this. I had thought I could give you much easier arguments for this. I could, but I thought about this morning. It would take me one lecture to explain what's in my head in an elementary way. And if you know a little bit of algebraic geometry, it's an immediate concept. So I think it'd be very interesting to give you a feeling where we are, if you're really interested in this, I'm looking at some of our third-year students here. You know, you write a thesis in your third year in every subject, physics, computer science, mathematics, it doesn't matter. You write a thesis in your third year. And I was talking to somebody yesterday. You start understanding something like this and you like it, then I will tell you there are natural continuations into an area where you can write a beautiful thesis, and even to an area of research. Jasper, I think, left for a few minutes, but he was telling me he would be interested in finding out what research is really like. And this is what it's like. You start out with something like the symmetric group, make a stupid quotient, you discover the Newton and symmetric polynomials. You understand that thing perfectly. You go to the next obvious thing, just a finite group action. You understand that thing perfectly, and you're moving very close to modern research. Okay. Okay, so I don't want to say too much more about it. Now what many people understood after they realized, so the names, keep in mind the name Frobenius. I'm a little bit of a German chauvinist here. A wonderful mathematician, Frobenius, who understood finite groups and finite group representations very well. And we were very lucky that there's this great mathematician of the 20th century, but rather early in the 20th century, named Hermann Weyl. You know the name from Hermann Weyl in physics. Hermann Weyl was a great intellectual, and he had the ability of understanding. It's very much like Atiyah, I think, Michael Atiyah. He had the ability to understand what is known. Yes. For example, he understood the averaging operator very well. He understood these pictures very well, and put it in a beautiful, beautiful description, and push it a little bit further. You see what I mean? This is not sitting down and saying, I solved Goldbach project. I solved, I don't know, some Poincare conjecture about spheres, or some deep thing. You see, you have to sit, if you're looking at a big, complicated individual problem, you have to develop new ideas based on that individual problem. Yes? But Hermann Weyl had knowledge of physics. He had knowledge of maybe even philosophy, and knowledge of mathematics and this kind of stuff, and he was able to see what it really means and apply it in a more general situation. Yeah? That is also very important mathematics and important science, right? You see what it means and apply it in a more general situation. Right? So Hermann Weyl understood what it meant and applied these ideas to the setting of compact groups. And I can't help but also mention, I'm a little bit proud to be associated with this group in France. I can't help but mention Eddie Cartan in this case. So these were people who made very deep contributions in the 20th century. Yeah? And even not in the late 20th century, but in the middle. 20th century. I didn't meet Eddie Cartan, but I knew he was the father of somebody I knew rather well, and so I mean you can see this is not so long ago. Okay. Compact groups. So I need to make a definition for you. So G is a compact, is a topological group. Let's make it a topological group. One is a topological space. Two, multiplication. So that's the operation, say, small k, small l. Let me call this thing k. No, it's G, it's a topological group, so it's not yet compact. So let's say G times H. This operation should be continuous. So we're imposing more structure, and the operation of inverse should be continuous. So the operation from G goes to G, G goes to inverse, G inverse should be continuous. Okay? Yeah, it's a topology space. It's a group. Everything you see that's associated with the group should be continuous. It's not so bad. Now, you might hack around, and you should probably hack around on the web and see if you can find interesting, horrible examples of topological groups. These things appear, the horrible examples, so the topology is ridiculous, I don't know, it's not ridiculous, it's something that doesn't relate to me too very much. It relates more to your teacher in Analysis 1, Kevin Malahakar. He understands these things over other fields and various things, p-adic things, that I don't understand very well. So if you're interested in this stuff, then talk to Kevin. Okay? So, but I'm interested in things that are not so bad, so I want to start with examples that I can relate to. And these examples are mainly what we call the classical groups. And I will tell you, this is what Hermann Weyl was thinking about at that time. In fact, he wrote a book which is more or less this title, and is one of the most fundamental books in this subject. I think it's called Classical Groups or something like this. Hermann Weyl. So I wanted to talk about these examples and talk about what sort of things they do, classical groups. So talk about classical groups. Let me emphasize, let me write the word here, classical. So classical, compact. Classical compact groups. Let's even abbreviate this thing, classical compact groups. Just for fun. Okay. When you hear the slogan, classical compact groups, you should understand that these things are exactly related to geometry. Geometry and analysis. But particularly, in my sense, to geometries. So I want to start with the first one. Recall in our lecture we started with the square, and we learned a great deal by starting with the square. We learned a huge deal by starting with the square. By starting with the square, we ended up by understanding the dihedral group action on the square. So that's a finite group, it's compact. But really what was very, very important to us in our discussion, we had this thing embedded in the for example, the affine space, this is affine 2 space, and we saw that the affine group over 2 space, say, over real numbers, is GL2R, semi-direct product, translation group. And now let's look at this thing. R2 is certainly not compact. And GL2R is also not compact. Also not compact. Let me just remind you, if you're thinking of GL2R, you should think of, if you like matrices, maybe you don't, but this is one way to think about it. If you look at the 2 by 2 matrices, so I always write that in standard basis, 2 by 2 matrices, that's the same thing as the transformations, all possible transformations. Here is 0, and here is a subvariety, maybe it's even singular, God only knows. It's called determinant equal to 0. All right. And it divides the matrices into 2 parts. That's just anything, that's just R4. And you have this equation, just for fun, let's write the equation. X1, X2, X3, X4. And so the equation is X1, X4 minus X2, X3. It's a quadratic equation equals 0. It's a real quadrant. So this is something that's separate. Here, determinant is negative, maybe, and here determinant is positive. And this is all of GL2R. All this stuff except for determinant equal to 0. That's highly non-compact. The complement of a surface right, it's really not compact. Okay. So that makes life tough. I mean, we really use the averaging operator. We really use a lot of stuff in the case of finite groups that we hope, as I was trying to explain to you the other day, we hope to generalize to something compact. I mean, by finding some sort of what we call measure on the compact group that, so we can do probability theory on the compact group. So these things are not compact. So you see, in the case of the affine, highly non-compact. The affine, there's no reason, there's no compactness built into this definition. It's just sort of a rough definition of the structure. But let's look at the first example. It's a little bit more complicated than the square. Okay, if you don't mind, let's look at the example of a sphere. And this sphere, let's look at this example. I'm going to call it M. The two sphere. The two sphere. We call this the two sphere. And let's embed it in R3. Well, everybody knows it because we live on the two sphere. Right. We live on the two sphere. And let's put it here, the usual two sphere. This is the usual two sphere. Here's 0. So M is the two sphere, say X, Y is X1, X2, X3. Coordinates in the standard basis in R3, so that X squared. So the two sphere without anything inside, X1, X2 squared, X3 squared equals 1. So we talked a lot about S1, and there the theory is Fourier theory. theory of S1 is Fourier theory. We talked about trigonometric polynomials and representation theory of S1. Here, this sphere, this two-sphere, is not a group. S1 was a group, but the two-sphere is not a group. So this is a sphere of radius 1. It's not a group. It's not a topological group. It's an interesting exercise to prove it is not a topological group. Let me just comment a classical but important problem. Which was posed and solved not so long ago. So a question, which spheres are topological group? For example, we have seen that S1 is an example. And we will see, in fact, today, that S3 is an example. So if I put the number up here, S1 is the one-dimensional, is a circle, S2 is the two-dimensional sphere, S3 is the three-dimensional sphere, and so on. And then the question is, what about Sm? What about Sm? It's an interesting question. Yeah. It's not such an easy question to answer. You might be amused by it, so you think about it. It can be transformed into algebra. And things of this type can be transformed into questions about so-called division algebras, classification of algebraic structures. Very nice. So it's an interesting question. What spheres are topological groups? This question, topology, in my mind, I would like to have a stronger condition. And I don't want to talk about it right now, but right now I'm just going to talk about the two-sphere. Remember what I said at first. Understand completely a basic example. Completely. The representation theory of the symmetric group is on Cn and the associated representation on polynomials. That is one example that Newton understood, I think. And if we can't understand that, then we have to quit. So we understand one example, and then we move, using some knowledge of group theory perhaps, to the same example, except for its general representation theory of finite groups on a vector space, arbitrary. What do they look like? What's the invariant theory? How do we do all this stuff? Does averaging give us everything? Are there analogous theorems here? Right? You will be coming close to research if you do that. Yes. Going around and talking about abstract mathematics or abstract physics or abstract computer science does no good at all. What does good is to really understand. So I like this expression in German, so from the Pike auf. So from the beginning up. I've heard from my colleagues in physics, there are bottom-up people and top-down people. Yes? I start from the bottom in some sense of my understanding. What the physicists mean by that is build a theory from the bottom up. I don't mean that. I mean start with examples and work with your own intuition and your knowledge from the bottom up. Okay? Not, yes? Okay. So let's, instead of starting from the square, let's start from the sphere. Well, I did talk about the circle yesterday, so let's start from the square. And then you ask the silly question. It's not so silly. What structure does the sphere have? What structure on the sphere? It's not a group. What is it? Okay. What is it? What is the structure of the sphere? Well, or how is it defined then? Well, how is it defined? So you write very slowly, the sphere, the two-sphere, is the set of points. Now, you have to make a step here. I wrote down this thing here, and this is what you see in school. Right? x1 squared plus x2 squared plus x3 squared equals 1. Right? Somebody told you that in school, and that does not help you at all. It does, in fact, does say that it's an algebraic object, because it's defined by an algebraic equation. At least that it does help. But in other words, we're talking about the geometry of the sphere. Why don't we say this is the set of points. Let's call this. Let's don't even write x1, x2, x3. Let's just write this is the set of vectors in R3. This is very good. So that the length of the vector squared equals 1. Okay. Isn't that a better definition? And then, even if you're just my grandson's age, he's going to ask you what all this stuff is, and you say, well, really what this thing has to do with, it has to do with the standard inner product I mean, he won't understand this answer, but you understand this answer with the standard inner product on R3. Isn't that true? If you look at the norm, this norm of the standard inner product, or some, I mean, you might want to change the inner product. I don't know. You might want to have an arbitrary inner product. But I think you would want to have a positive, definite inner product. You would make sure this norm is positive, and then probably, except for little, I mean, you might want to weight these things with numbers, lambda 1. These numbers are often called eigenvalues. You might want to weight the norm with some weights, but if those numbers are positive, you might like physics and you get relativity theory. But let's get a sphere. Otherwise, if it's relativity theory, you might get a hyperbola, and therefore it might not be compact, right? You know, x1 squared minus x2 squared is not compact. Equals 1. It is not. Okay. You know this. That's a hyperbola. Right? Right. Right. You're looking at that. I'm happy you're looking. Then you're smart enough to make change of variables and call this y, so this is y1 times y2 equals 1. And you know that that is something like that, right? You're gonna, yeah. So you know, right? So that's what happens. That's what happens basically with all these physics guys who are doing relativity theory. They get things like that, and what they get is non-compact things, right? But if you get a usual positive definite for this norm's positive definite, then you're going to get compact things. Okay. I know the sun is coming there. I hate to. Yeah. Did that do it? A little bit more.
Start searching.
Oh, he has to do it.
I think it's that curtain. Well, it's got.
you're a physicist, you should know what the angle of the sun is. Oh, okay.
Well, it's gone, so.
Okay, so the inner product is the thing that we're talking about here. And so the good transformations, the sphere is defined by the inner product. So the question is, what are the appropriate transformations? What's the group? Just like we asked for the square, and I claim it should be the ones that they should preserve the inner product. And therefore the norm. And then you ask the question, what are those transformations? Right? We've asked this question before, right? What are the transformations which preserve the inner product, or would preserve the norm? So, in other words, we have a question, or a project, characterize the, let's make it a little simple. Let's say it acts on the ambient space. Let's characterize the transformations. There are symmetries, but now we're using the word transformations. Phi from R3 to R3 with phi, I'll write it in a naive way. You move a vector with phi, and you don't do anything with scalar product. Isn't that the obvious question here? All right, if you're not doing anything with scalar product, those transformations will stabilize norm 1. That means they automatically stabilize the sphere. S2, because they preserve the norm, and so they preserve norm 1. So they stabilize the sphere. So these transformations act on the sphere. Okay. So I think we have come to a hard problem. I didn't say anything about these transformations. They could be continuous, they could be horrible, they could be anything. So the question is, what? I didn't say anything about it. It's the same problem we reached in the case of the affine group, right? It's almost exactly the same problem. What stabilize the lines, what stabilize, or the orthogonal group? I don't know the answer to the problem. Probably you know it someplace, you people who know the literature. What regularity do you need here to prove that such a transformation is linear? Yeah, I don't know. Yeah, I don't know. I'm not sure. Maybe my question is so this project leads to a question that I would have: what regularity is needed? I didn't say anything about it. What regularity? Does it smooth differentiable? What regularity is needed here to prove that such phi is linear, and that would mean in GL3R. Probably you need something, I don't know for sure, this may be a very fine question if you're interested in this question. It's very easy to read around on the internet what is known, right? And then we can discuss it, okay? But that's a question sort of for the future, you know, excuse me. It's a question that is sort of, there are beautiful expressions in German, by the way, which is the kind of thing. And you say, das ist aber Zukunftsmusik. Future music, right? Because we're not, right, wouldn't you agree? We're not in a position to understand that question really, but it's a question that you can note. Keep it in the back of your mind. Das ist aber Zukunftsmusik. Yeah? And it's an interesting question, maybe. Maybe it's not. Maybe it's a trivial question. I don't know. Anyway, it would be good to find out what is known. That's the nice thing. If you go to graduate school at a serious place, there will be professors hanging out who love such questions and will know exactly what's going on. And you go to these professors and chat with them about these questions or with your friends, and you immediately have interaction on research level science. Right? That's the reason you want to go to an active place of research. Right? Isn't it true? Right? Doesn't matter whether the place is famous or whatever. The key is, are the people there willing to talk to you and have fun doing mathematics with you and talking about interesting questions like that? And, or is it just a bunch of people hiding behind their desks and yeah. Anyway, that problem is probably Zukunftsmusik. So we then write a small project small, characterize the group of linear transformations T from R3 to R3 in the standard coordinates, which preserve the inner product. The standard inner product. Let me say, put standard down here. So we have such a thing, and we that means that TV, TW equals VW for all VW. And you can check as an easy exercise if you haven't done this exercise before, it is that TV, TW equals VW. In other words, the full inner product is preserved if and only if the norm is preserved. You only need to preserve the norm, it turns out. You only need to, it's very interesting. In order to preserve angle, which the inner product gives you, and norm, you only need to preserve the norm. Isn't that interesting? Right? You only need to preserve the norm. Okay? And in the jargon linear algebra, which you might not be familiar with yet, this is the same, and you definitely need to understand what the adjoint operator is of an operator. I will not bother you with this, but everybody in physics knows about adjoint operators, right? So this is the statement, this equals VV, whatever that means. And so the equation for T is T star T equals the identity. Okay. Just accept that. You can just write it down. You don't need to know what you're doing. It's just that I told you this because you ought to learn what an adjoint is. If you haven't seen it, you probably didn't see this in this Mickey Mouse linear algebra that you were forced to take last semester. Although Professor Bancroft is a very good professor, he has to teach to 150 students, so it's ridiculous. But when he's lecturing to you this semester, you will, I think, hear about this thing, what this thing really is. It's really the transpose of the matrix. So it's not so bad, okay? And this is the equation. Okay? And it means that in the standard basis, which is an orthonormal basis, the standard, and this basis, as you know, is an orthonormal basis. They're length 1 and they're perpendicular to each other. And the standard orthonormal basis the matrix of T, I talked about this before, looks like this. TE1, TE2, TE3. This is the first column is T of E1, the second column is T of E2. This is standard in matrix. Third column is T of E3, right? And these things are perpendicular. So T, E, I, T, E, J is either 0 or 1, and so we write that delta Ij. And that is the formula for a matrix in this thing. You check it. I talked about it before. Okay? Not so bad, right? Okay. Well, this says that T of E1 has length 1, T of E2 has length 1, and T of E3 has length 1. And so, you're not stupid. You write down where those things are. This triple, be fearless. You see, one of the problems that people in mathematics are beginning, they're afraid. So you write this thing down. That's really the matrix, but it's just a triple of these things. And that is a point, T of E1 is a point of length 1, so it's in S2. T of E2 is a point of length 1, so it's in S2. T of E3 is a point of length 1, so it's in S2. Right? So the statement that all these things have length 1 is a statement that these things lie in S2 cross S2 cross S2. So there's a map there's a map from the matrix of T to S2 cross S2 cross S2. So we have T goes to the matrix of T, goes to S2 cross S2 cross S2. Now, when you're beginning doing mathematics, you ask the stupidest questions you can ask. What remarks can you make about the product of S2 cross S2 cross S2? the most elementary topological remark possible. It is compact. Obviously. Product of S2 cross S2 cross S2 is compact. S2 is compact, therefore the product is compact. It is compact. Right? So I realize the point in this isometry group, we might call it, gets mapped to this set here, S2 cross S2 cross S2. Now, you have a condition here on this operator. That is a condition that not only is it length 1, but it is a condition that these things are perpendicular. Right? These things are supposed to be perpendicular. Right? So we have the condition in S2. Let me see here. I'll write here the condition that it's perpendicular. Right? So let me see here. This is what Prabhat's talking about at dinner. Is just write down coordinates and see what's happening. I think you're absolutely right. Right? So if we have something in the first thing that's x, oh, terrible. Let's say here x1, x2, x3 is in the first S2, and y1, y2, y3 is in the second x2, and this is where Prabhupada's right. If you just write these things down, it occurs to you what's going on in the third S2, and this is supposed to be perpendicular to that, so I start writing questions. X1, Y1, X2, Y2, X3, Y3 equals 0. That's not so bad. That's intersection of S with some very reasonable set, and in particular is closed. And then you have the other one, X1, Z1, terrible, huge number of equations. X2, Z2, X3, Z3 equals 0. That's X, where X1 is involved, perpendicular to Y, that one and that. Oh, we only have one more equation. So Y1, Z1, I think I got all the equations here, right? Y2, Z2 plus Y3, Z3 equals 0. Right? That's it. Vectors of length 1, which are orthogonal to each other, that is a subset here of the product of 3 spheres. Except it's like this horrible assistant of Trump, who's named Mulvaney, when he just says, he was explaining what Trump was doing in bribing Ukrainian people. No, you're not Ukrainian, unfortunately. Yes. This guy Mulvaney says, accept it. Deal with it, he said. It's standard. So deal with it. Deal with this. Think of Mulvaney, just think of this. Deal with this. Yeah? You have to go in higher dimensions to understand something. Yes? So what you have done is you have embedded the space of matrices of this group that's irrelevant in the product of 3 spheres. However, in the product of 3 spheres, it satisfies 3 equations there. So we can say that the 3-dimensional orthogonal group, now that is going to be the isometries that we're talking about here, I think I've used the notation, is embedded in the product of 3 spheres, S2 cross S2 cross S2, and defined there by these equations. Isn't that right? Length 1, length 1, length 1, orthogonal, orthogonal, orthogonal. Not so bad. Isn't that wonderful? You have observed that it's a closed set. I mean, the level set of equations is a closed set. It is a closed subset of the product of 3 spheres, and is therefore compact. It's much better than compact. It's in product of 3 spheres defined by three beautiful equations, we even can say that this is a compact manifold. It's defined by smooth, in fact, algebraic equations in the product of three algebraic spheres, and we can call this even an algebraic manifold. So anyway, it's in particular O3 is compact.
Smoky, smoky, smoky.
That is the first, in my mind, classical group that you would probably consider. So-called classical orthogonal group, namely the linear isometries of the two-sphere. Okay, so that's a little research project that we started, and anybody can sit down and generalize that and come to the first basic compact group, namely the compact orthogonal group ON. Recall how this all started. It started by our naive consideration of the sphere, the two-sphere. So, the first classical compact group, in the words of Hermann Weyl, classical compact group 1 is the orthogonal group ON, which is the set of operators in GL n plus R1 R, so operating on the sphere, such that the inner product is preserved so that norm of the standard inner product on a vector is preserved. That's enough. Norm is preserved for all V in R n plus 1. This is called the classical, yes.
Why do we now take, just with the notation that we had before, do we also say that the
You're talking too fast for me, what?
that ON is, or O3 is in GLN3
Yes.
and not n plus 1?
Oh,
Why is it?
oh, I probably made a mistake here. I did make you're being nice to me again. It should be ON plus 1.
Yeah.
That's what, I'm sorry. Yeah. I get mixed up because I think of it acting on the n sphere, but you really need to think of it acting on n plus 1 space. And n plus 1, and since this is everything over the reals, I think sometimes I would write, well, I'm writing script here, I don't mean to, ON plus 1 R. Because in principle I can do that. In fact, what I really could do is write the orthogonal group on a vector space equipped with an inner product. All right? And maybe you should, and now you see if I allow this inner product to have mixed signature and all sorts of things, we get interesting relativity theory and so on. But here, the classical group is for the positive definite norm. So we don't want to allow negative norms. Okay.
Question. Sorry, question.
Yes, Martin.
The orthogonal.
You're also quiet. Everybody. I'm deaf and everybody's quiet. What?
the orthogonal group over mixed signature quadratic form, is that also compact or?
No.
No. Okay.
So I'm glad Martin asked if you have a mixed signature, so the quadratic form is not necessarily positive. In fact, say mixed. For example, well, to answer Martin's question carefully, he asked about the mixed signature scalar product. So if we write down, for example, xy equals x, no, let's even just write down the norm of x, possibly mixed signatures. Now it's a question of tradition, but in fact, the best notation is x1 with a minus here, x1, xq with a minus squared, and then the plus ones at the end, so xq plus 1 squared plus x q plus p squared. Martin's asking about this form. You know, see, I wrote down a norm here in standard form. So this would be, you say the signature of this thing is PQ, but the best way to, from the point of view of working with this stuff, the best way to do this is put the negative stuff first, actually. You guys in physics don't like to do that, but I do this. Is somehow there's a reason to do this. I can't tell you why. It makes life easy. So this is the signature is PQ, and then what Martin was asking about, you should write OPQ. And maybe emphasize real numbers, ORPQ. Okay. So on the vector space of dimension n, in other words, P plus Q is equal to n. So in relativity theory at the beginning, P plus Q is equal to 4. Right, Q is equal to 1, P is equal to 3. I think, is that the signature? You get the orthogonal group OPQ. Okay. And maybe this is the standard norm of a standard PQ norm. And this is what we deal with. So to answer his question, OPQ is compact if and only if P equals 0 or Q equals 0. So if and only if it's either negative or positive, but not mixed. The minute it's mixed, it is not compact. Okay. And you should have feelings it's something like a hyperbola. You see, that's what we were talking about. You see, negative and positive, you put together, you get what we were talking about before. But just keep in mind what I said to him before. X minus this is x1 squared minus x2 squared. You see, and this is really a hyperbola. So if you have mixed signatures, you have all these hyperbolae going around. Right? This is the reason you have heard the word hyperbolic geometry. Okay? So this is the OPQ, and it's very nice that Martin asked this question. I don't want to dwell on this. This is much more complicated. This one here is not so bad. So let's talk about the action of K. Now I will just call it, because I'm just trying to be a little bit more general, K, which I'm talking about O, and if I just write O-N, so O-R-N, so the positive definite standard thing on the sphere. Now somebody corrected me here, it was Nicholas. So if that's really O-N, that's, oh I see, this is on the sphere Sn minus 1. right? Because it's ON is acting on an n-dimensional space and it acts on the sphere. Right? Ah, that question's too big. It's typical of me. Let's even ask about what about O3? Sounds like a telephone company, O2. So O3 on, call it K, on the 2 sphere. What about it? Okay. Because we can draw a picture. And I'm going to talk about this in terms of matrices. So here is the, well, maybe not matrices. Yeah? Here is a point here. Let's start here with the base point, x0, on the 2 sphere. It's too bad that these Vietnamese guys aren't here today. They're very good at telling me about the orbits of it. And what about here? What about here? What is this thing? This is x0 is the point North Pole. So it's, what is the North Pole here? Maybe it depends on your axis. Maybe it's something like this, right? So maybe this is the point 0, 0, 1, right? That's the z-axis maybe, and that's the North Pole, right? So, and now the question is, so that corresponds to the vector E3, and right? And now we take another point over here, and we ask the question if we can map 0, 0, 1 onto this other point. So let's see here. So we ask the question, this is another point, let's call it x. So can you map x0 onto x? So in other words, I'll write it here. We're talking about the action of this group. Is there some transformation in the orthogonal group in here we are, O3, so that with t of x0, the top point, equal some other point, x, some arbitrary point. It's a reasonable question, isn't it? Can you get everything? Right? In other words, is the action transitive? Right? It's a reasonable question. Well, you say it's a stupid question, maybe. So t of E3, you put down the vector x. So this is x here. This is x. X is this column vector. Right? Now, I know you had to take this Mickey Mouse linear algebra, but if you have an ortho, it's called basis extension. If you have one vector, right, and you want to complete that to a basis, yeah, so that you want to complete it to a basis. So maybe you should not think like this. You have one vector, and it defines a line. For example, here's x, and you want to complete it to axis. What you usually do, I mean, it doesn't matter. Auf Deutsch heißt das Basisergänzungssatz. So you extend things to get a full basis of the whole place, right? And so, but what you would do, you're not stupid. What you could do here in this situation, you could take a plane which is orthogonal to this line, this plane orthogonal to this line, and then in this plane, you take an orthogonal basis. Yeah? Why not? Okay. So take the line, and in this plane, take an orthogonal basis. Let's say the orthogonal basis is V1, orthonormal basis, E2. You can always do that. So I put here T of E2 is, say, here it has V2, and T of E1, this column vector here, is V1. Got it? It's called completing the basis. You have, right, you have one base thing, and now you take an orthogonal plane to that, right? And then in that orthogonal plane, you take an orthonormal basis, and therefore what you constructed is altogether an orthonormal basis, B1, B2, X, and this was X, and this is a matrix in, this matrix is obviously in O3. Any questions? You can see I've done this before, and maybe you have not done it before, and if you haven't done it before, you should do it a lot. Okay? This is the way you do things. Okay. Very easy to deal with matrices. There's no, you should do it. Think structurally without matrices, but you can very easily make computations with matrices. So you proved here that O3, which I'm calling K, acts transitively on S2. So you should move into the good notation. You should say S2 is a K homogeneous phase. That's very interesting. S2 is a K homogeneous space. And I'm particularly talking to physicists here, because this appears all the time in physics. You have phenomena going on, for example, on the two-sphere or higher dimensional spheres, and you use the fact that those spheres are homogeneous, and I'm going to explain why. So what is the picture? The picture is this: K is equal to SO, SO is maybe you want to say O3, R. We have the action that I talked about on the two-sphere, and this is a transitive action. Okay. That means if you take a point on the sphere, so I took x0, the North Pole, it doesn't matter which point, but sometimes let's take x0 to be that point just for fun. Take the North Pole, yes, and you get everything. The orbit of the North Pole, or the orbit of anything you want, is everything. It's transitive action, I just proved it. Okay? That means this is an orbit. That means, in every sense of the word, S2 is equal to K modulo L, where L is the isotropy group of that point. Didn't I talk about this 3 or 4 times in the past lecture? If you have an orbit, then the orbit is G modulo isotropy acting on the right. Right? So what you should think is picture K. This is K. This is K modulo L. I don't know how many times I have drawn this picture. I've drawn it with the permutation group. I've drawn it abstractly with just continuous quotients. I've drawn it all over the G modulo H orbits. That appears everywhere. If you want to understand anything in this subject, you need to understand G modulo H. Right? The sphere, I mean, this happens to be the sphere, but since I know that, I don't even care whether it's a sphere anymore, I'm done. This is K modulo L. That means that you have K, and you have x0, for example, and what lies over x0 is the isotropy group x0, so I'll write it here. Here is the identity. This is the isotropy group at x0, and it lies over here. And this I call L. Okay. Yes.
Is there anything or is this actually not free? Or, well, it should be free.
Well, if I have a big, of course my picture claims it's highly non-free because I have this big isotropy. I mean, it's a very good question. It would be great if it were free, which might be possible theoretically. I agree completely. Then you would say the sphere itself is a group, because you can identify it if you have a free transitive action. It would be a group. Now, in fact, it's not at all possible. And secondly, I'm going to compute the isotropy now. Okay, so you will really see that it's not free. Right? Okay. If you don't mind, I'm going to change x0. The usual people who write this thing down have x0 to be this point. It doesn't matter whatever point it is. I'm going to change the point to make it the matrix look in a form that people you might see on paper someplace. So it doesn't matter, but okay. So let's try to describe L. That's what Nicholas is. Why is it not trivial? I mean, maybe it's completely trivial, but I'd rather say, okay, I want to really describe all of it, and it's going to be big. You can imagine we could compute the dimension of the orthogonal group. We could commute the dimension of the sphere, and you can see that the orthogonal group is much bigger than the sphere, and so it has to be big somehow. Right? So we want to describe L. Okay. And so here we go. Here's a matrix. So let's take a transformation in L, and let's take its matrix of this transformation. And here is E1. E1 is in fact, this point is now E1 the way I took it. It's going to be look a little bit nicer. E1 has to go to E1. Right? Because it has to be fixed. So the condition here is T of E1 equals E1. Okay, so that's great. The first column of this matrix is that. Now, Nicholas is happy already because that's a mega condition already, right? Okay. Secondly, the second, we have to know where E2 goes. I don't know. I'm done here. That's enough. That's the only condition. But E2 has to go to a vector which is orthogonal to E1. Right? That's the condition here. So that means that this element here is 0. And this element similarly has to be 0 because it has to be orthogonal to E1. And usually we put a block here, and I'll just call this matrix A. Or maybe I'll call it B. And there's no condition. Oh, well, there is a condition. Because, well, let's call this matrix B. But let me write it down. B1, B2, B3, B4. Right? And now we need maybe a condition on this. because it's automatically orthogonal to the first thing, that's good, but it may not be orthogonal to each other, so we certainly need B1, B3, plus B2, B4 equals 0, that's the orthogonality here, right? And so the point is, B is in O2. Right? Right. So you have a wonderful fact here that even we can use to make advertisement for the telephone company O2 in Germany, that that O2 is the isotropy of the base point in the sphere of the O3 action. Right? You can see that being a wonderful ad on television. And, right. So it says that the two-sphere is equal to O3 R modulo O2R acting by this way. Okay. So, by the way, O2, look at the condition on O2. Oh, why did I, yeah, 0. And these things are length 1. Oh, I hope you know, O2 we already talked about, didn't we? O2 was the rotations and reflections, remember? So, from the point of view of dimension, O2 is dimension 1 over the real numbers. It's a circle basically, except it's rotations acting, and the sphere is dimension 2. So the dimensions have to add, so that says the dimension of O3 over R is, that's two-dimensional. 2 is, and that's O3 over R, dimension of, that's O2, and sphere is two-dimensional. So this thing has to be four-dimensional. Right? 2 times 2 is 4. Right? If you don't believe me, think of this picture. Upstairs is O3. O3 fibers with fiber O2 over the sphere. Right? So all of these things are two-dimensional. And the base is two-dimensional. So the upstairs O3 is four-dimensional. Okay. So then you could have fun. You want a formula for the dimension of ON. Okay. So ON, not really ON, ON plus 1, say. Same argument, modulo ON on the right action, because it is the homogeneous space Sn. Yes. So it says the dimension of ON plus 1 equals the dimension of the sphere plus the dimension of ON. And that is a recursion formula for the dimension of the orthogonal group. Right? It's a recursion formula for that, right? Yeah. And if you do this recursion formula out, I think the dimension of ON will be, this should imply, I think, if I'm not mistaken, this dimension is n times n minus 1 over 2. Yeah.
So we add up the dimension of O2 plus the dimension of S2, and that should give us the dimension of O3.
That's
Oh, no,
of O3. Did I write something stupid on the board?
Like the sum 1 plus 2 is 3.
The dimension, so the dimension's that, so the dimension so what we should have here is the dimension of S2 equals the dimension of, I'll do it maybe in a nicer way, dimension of 3 minus the dimension of O2. Maybe that's the most intuitive way of looking at it, because with O2, you cut out the S. So I think what we said is the dimension of O3 is equal to the dimension of O2, which we've seen to be 1, plus the dimension of the sphere, which we've seen to be, which is obviously 2, so this thing is 3.
Oh, okay. So it was
Actually,
was a typo up
Did
there.
I write something wrong up there?
You wrote forward.
Okay. Oh, yeah, I wrote 4. Why the devil did I ever write 4? 3. You check that I haven't made a mistake. Yeah, I think that's okay. Yes, this is okay. Okay. This is a very important group for quantum mechanics. Okay. And starting with the sphere, we ended up with which is important for quantum mechanics and for many things in mechanics. And many problems which exist on the sphere, what you do is you go upstairs, solve the problem, discuss the problem in the group, start on the sphere, go to the group, do something in the group, go to the matrices, do something in the group, and solve something, and then come back down. Let me mention a classical, very important problem that is viewed in that way. And you're going to have to help me, German people, because I can't translate. I don't know. What is a Kreisel of English? A top? Is it Kreisel that thing that you... Yeah, it's Kreisel is the top, right? You pull it and it spins on the... Yeah. One of the fundamental problems in the beginning of dynamical systems is to classify spinning tops, the dynamical systems of spinning tops, which have certain symmetry. Right? Lagrange asked this problem. I don't know who solved the problem finally. Maybe
Klein? Felix Klein?
who's speaking? What?
Felix Klein, I think.
I don't think
Klein
so.
and Sommerfeld in the...
Euler, there's something Euler and
Well, Euler and Lagrange certainly understood the problem. It started there and was understood, solved later by some other people. Classified spinning top. There was a last example that was needed to be understood. What is called completely integrable spinning tops. If that makes any sense to you. And well, a lot of the way of working on these things is to go into orthogonal groups like this. Let me, before we make the pause to this afternoon's lecture, let me consider another geometry. Okay? Let us not stick to the reals. Let us go to the complex. Numbers. Every physicist in this audience knows that you will go to complex eventually. So let's start with complex. And so let's go let's go to the vector space, the complex vector space, C2. We just were in R2, let's go to C2. Okay? This is where everybody works in physics, in complex thing. This is where I work in complex analysis, right? So recall what if we have Z W here, then the standard norm of that pair ZW, Prabhat, this is dedicated to you, is absolute Z squared plus absolute W squared. That's also the real norm, right? But the good way of understanding it is in complex notation, absolute Z squared plus absolute W squared, right? And then the question is, describe, this is the project again, it's not a question. The project is describe the transformations T. Now, you're in C2, so you want to preserve the complex structure. So in GL2C, so the linear transformations of the complex vector space, which preserve this norm. The norm. In other words, norm squared, you don't do anything to it. It's the same problem, almost. Right? Almost the same problem. Yeah? Well, those transformations are called unitary transformations. And if you are accustomed to thinking about the complex plane, so for the vector space V, the one-dimensional complex plane, then the norm of Z squared is equal to absolute value of Z squared, and the one-by-one matrix or the linear group is Z goes to lambda Z, and it needs to be preserves it. The norm in the one-dimensional case, whenever, so norm Z squared equals norm lambda Z squared, it shouldn't change the norm, and of course the lambda comes out in front, so it says that the lambda squared equals 1, so it says that the unitary group on the plane is just the rotation group S1. So let's write it down. The notation is the unitary group 1 on the plane. That's the easiest thing, but maybe we'll do 2 in a minute. Is as a geometric space, the sphere, the circle. So this is an example where a sphere is a group. We know that. It's the one, and you should think of it as the unitary group. It is the thing that preserves this norm. Okay. Well, let's look at U2. Okay. We should have fun going. We'll go to lunch just after we understood U2. Me too, you too. It's the U2 movement. So, yeah. In some sense, isn't that right? All these sexist, horrible guys, it should be U2. I don't know whether you agree with that. You two. You're the guy who's, I'm not pointing at Prof. Come on. He's certainly not a sexist guy, right? But you should, Harvey Weinstein, you should point at you two. You two should go to jail, right? Okay, U2. So let's look at U2. So an element is in U2. If and only if. Well, let's write the matrix of it. Matrix of this thing is equal to AB AB, this is T of E1, and CD. All right? Isn't that right? Yeah? And now what should be here? So, the norm of, I'll write it down. This is a vector v, I'll write this thing as a vector v, and this is a vector w. The norm squared of v should be 1. The norm squared of w should be, this is w. The norm squared of w should be 1. And the inner product associated to this norm, the inner product associated to this norm should be 1. 0. They should be orthogonal. Now the inner product of ZW, I don't know if I've written it here, no, that you write the correct inner product, and this is what we're discussing with Prof a little bit, right? The correct inner product should be, after you write down what it should be Z1W1 bar plus Z2W2 bar. This is the inner product that gives this norm. I think this is your argument for this inner product, basically, right? No? For the naturality of this inner product. Yeah? Okay, so it should say that the norm of the first one is 0, so this means that absolute a squared plus b squared equals 1. Right? That's the norm. And absolute c squared plus d squared equals 1. But a c bar plus b d bar equals 0. Okay? And now that condition is a very strong condition. The condition that here is you have this vector, this complex line, and you have orthogonal complement to this complex. This is the point AB, and this, or which I'm calling B, and this is the point CD, which I'm calling W. Right? So you're in two complex dimensions. It means that these have to be orthogonal. With this, it means there's almost no choice. You can have two choices, really. Well, wait a minute. Remember, we had two choices. You go that way or that way. This is a complex line here, right? How many choices do you have? A whole circle of choices, right? So you make one choice, and then you rotate it by a circle. Okay? So this is the good choice is AB with norm 1 and minus, let me see here, B bar, I hope the right answer is minus B bar, A bar. Is that vector orthogonal? A times the thing bar is AB, and B times the thing bar, right? So that will be orthogonal, and then you allow a rotation in here, which accounts for going here. So look at that right there. That is, well, look at the determinant. The determinant is a squared plus b squared equals 1. That's the determinant. So this thing has determinant 1. This is this is the length of that vector. This guy here is in the sphere S3, which is the unit sphere in C2. Right? It's an arbitrary element of the unit sphere in C2, and you just have to rotate it by a rotation here. This is the two-dimensional unitary group is the two-dimensional unitary group with determinant 1, which we call SU2, times a possible rotation, which we see here, rotating around this orthogonal point. And it's very interesting. It's a two-dimensional unitary group with determinant 1, which is what everybody uses, really. You make the determinant equal to 1. Usually you kill this rotation that you have here. This rotation, called by the physicists quite often phase. So you kill that, and if you forget that, then you have a wonderful thing that SU2 The unitary operators of determinant one is really the three-sphere. That is incredible. Three-dimensional sphere is a group, very unusual. So the one-dimensional sphere is a group, three-dimensional sphere is a group. Are there any more? You might be interested in thinking about that. Okay. To tell you just the history of this, the sort of modern version of that question was solved by Sayre in his thesis not so long ago, in the early 1950s.
Sorry, is it not Milner, the classification of associative algebras?
Pardon me?
Was this not the classification of associative algebras? So
I'm not hearing you say it.
wasn't that shown to be equivalent to the classification of associative algebras? That
Yes,
was
but I'm saying the final version of this question. So this question, in some sense, is solved by the theorem of Wedderburn. But when I'm talking about, to answer your question, I said the final version of this question was parallelizable spheres, because you see the tangent bundle of a Lie group is trivial. So you're asking really whether or not a sphere has trivial tangent bundle, and there were some very non-trivial questions related to that, which caused very modern developments in many subjects. This was somehow very closely related to the thesis of Jean-Pierre Sayre. I think the thesis. You never know. I don't know what happened first, but in the early days of Sayre's work. Yeah. Okay, so it's an interesting question. Even the question of topological groups and so on. Okay. See you this afternoon. Thanks for your patience. So I have some idea.